All right, let's jump right in. Welcome to today's Explainer, where we're going to unpack one of the absolute most critical, foundational steps in natural language processing, or NLP. You see, if you're building an AI pipeline, training a machine learning model, or even just trying to figure out how search engines and chatbots work behind the scenes, you inevitably crash into the wonderfully messy reality of human language. Before a machine can do anything genuinely intelligent with text, it needs that text cleaned up and standardized. So today, we're focusing on exactly how we do that by choosing between two heavyweight techniques, stemming and limitation. Here's our roadmap for today. We'll kick things off with the text normalization problem, then meet our first contender, stemming, the fast chopper. After that, we'll look at limitation, the smart linguist, before throwing them head-to-head in the great NLP face-off. And finally, we'll give you a concrete framework for making your choice. Section 1, the text normalization problem. Taming human language. Okay, before any complex algorithms can analyze our text, we have to deal with the fact that human communication is incredibly fragmented and highly inflected. Seriously, think about this for a second. How do machines actually understand that running and run mean the exact same thing? As humans, we just process this instantly, right? We use context and a lifetime of language exposure. But a computer? It just sees two completely different strings of characters. If a machine treats every single variation of a word as a totally unique data point, the computational power required to process just a simple paragraph would be astronomical. It creates a ton of noise and inefficiency.
Well, that brings us to text normalization. This is the essential pre-processing step where we clean and standardize text. Languages like English are packed with thousands of derived or inflected words, basically words that originate from a common root but have different endings based on tense or grammar. Normalization is the process of stripping those variations down to their common base form. Doing this cuts through the noise, groups similar words together, and drastically reduces the computational power the machine needs to actually process the data. It's the crucial setup step before the real AI magic can happen.
Moving on to Section 2, stemming, the fast chopper.
Let's look at the most straightforward way to solve this problem. And what's really interesting here is just how incredibly simple this algorithm is. Stemming is essentially a normalization process that relies on hard and fast heuristic rules. It doesn't actually know English. Instead, kind of like an overly enthusiastic lumberjack, it just blindly, but super efficiently, hacks off common prefixes and suffixes from the ends of words. So running becomes run. Jumps becomes jump, swimming becomes swim. It's a fast, aggressive chopper that reduces words to their core stem so they can be easily grouped together in a database.
But as you might guess, because it's just following basic chopping rules, it has a major flaw. This example perfectly illustrates a problem known as overstemming. If you feed the words history and historical into a stemmer, the algorithm just chops off the endings and reduces both of them to history with an I at the end. Now, history is obviously not a valid English word. The stemmer just doesn't care about grammatical correctness. It only cares about matching the essential meaning of words as fast as possible. For a lot of tasks, that's totally fine. But it does mean you lose actual linguistic accuracy.
Which brings us to Section 3, lemmatization, the smart linguist. Now, if you need true accuracy in real words, you've got to turn to our second technique. Lemmatization doesn't just blindly chop words like a lumberjack. It's a highly methodical, multi-step linguistic process. Step 1 is tokenization, breaking the text into individual words. Step 2 is absolutely critical, POS, or parts of speech tagging. This assigns a grammatical category, like noun, verb, or adjective, to each word, because a word's base form often depends entirely on its role in the sentence. And finally, step 3 is the actual lemmatization, which uses those tags alongside a real dictionary or lexicon to pinpoint the true valid base form of the word, which we call the lemma.
The absolutely crucial takeaway here is that lemmatization actually preserves true semantic meaning. Because it uses a dictionary lookup rather than just hacking off letters, it knows that the base form of the adjective better is actually good. It also knows that history is already a valid root word and leaves it exactly as history, totally avoiding that weird historia error we saw earlier with stemming. It handles irregular verbs and complex grammar with total precision.
All right, Section 4, the great NLP face-off.
Now that we understand how both of these work, let's put them in the ring together. It really boils down to the fundamental trade-off you constantly have to manage in NLP, speed versus accuracy. Stemming is fast. It uses basic heuristic rules, completely ignores grammatical context, and doesn't care if it spits out non-words.
It just gets the job done quickly. Lemmatization, on the other hand, is significantly slower. It requires parts of speech tagging and a constant dictionary lookup to preserve valid words and their exact context.
I love this quote from our sources because it completely hits the nail on the head regarding their philosophical difference. Stemming is a purely mechanical operation, just removing prefixes and suffixes. Lemmatization is a cognitive operation, actually understanding the root form of words. Creating a stemmer for a brand new language is relatively easy because you just write a quick list of chopping rules. But creating a lemmatizer for a new language, that demands a massive amount of linguistic comprehension, vast text corpora, and deep structural rules. And finally, Section 5, How to Make Your Choice. Okay, abstract concepts are great, but how do you actually apply this to your own machine learning pipelines? Here is your key takeaway framework. If you're doing sentiment analysis, say sorting through thousands of restaurant reviews just to see if they're generally positive or negative, you just need the base words fast. Stemming wins. If you're doing spam detection on millions of emails, same thing. You just need broad patterns quickly. Stemming wins again. But if you're building chatbots, conversational AI, or question-answering systems where the machine actually has to output readable human text or deeply understand the nuance of a user's question, you absolutely need real, valid words. In those cases, lemmatization is the clear winner.
Oh, and here's a really cool advanced pro tip if you find yourself stuck between the two. You don't actually have to choose just one. If you have an absolutely massive data set but still need high accuracy at the very end, consider a two-step hybrid approach. You can use the fast chopper, stemming, for your initial massive bulk data reduction. Then, once you've filtered that down to a smaller, more relevant data set, you can apply the slower, smart linguist, lemmatization, on that refined set to ensure perfect accuracy right when it matters most.
At the end of the day, mastering your data preparation is basically the hidden secret to any successful NLP project. An AI is literally only as good as the structured data it learns from. So I'll leave you with this to chew on. Whether you choose the blunt efficiency of the fast chopper or the deep comprehension of the smart linguist, how are you going to prepare your data to build a flawlessly structured AI pipeline? Think about your specific use case, weigh your need for speed against your need for accuracy, and build accordingly. Thanks so much for joining me on this explainer, and keep learning.